downloading. So you can download it from Microsoft. Just Google for Visual Studio. Not the code, because we need the real one somewhere. Yeah, Google is much better than Bing. Yeah, it gives you the right result instantly. And the community edition is free of charge. There is only one minor annoyance, that after 30 days it will ask you to sign in with a Microsoft account, but those are free of charge, so you can just create a disposable account if you don't have one yet. There are also informations on the internet how to bypass this and just not sign in. So we download the installer, we execute it. The installer needs internet connectivity, since it's just a online installer, so it requires the internet to download all the other components, and we only require here the desktop development with C++. And I would always recommend to install it in English, because if you have any troubles, any error messages, and you try to look for them on the internet, then you will most likely find English results. So if you have a German error message, that's pretty useless usually. So I always go for the English version. There are a few components which one might want to add, but for our use case we really just need the bare basics. So just press install, and this thing will then proceed installing until it's done. It takes about 15 minutes to half an hour, depending on your internet connection. With a faster connection, of course, it can be shorter. But we will not be waiting for this to complete. We can leave this complete on this virtual machine in the background, and I will just switch to another VM I already set up earlier, where we have it installed. Generally, Visual Studio, the way it looks, they updated it and modernized it. I like a few older layouts, so there are settings you can change if you prefer a less modern style, but this is not part of the lecture, so you can just customize them. If you have any questions about customizing the UI, you can ask me as well. I see we have one more participant. I shall update the attendance list accordingly. Okay, so once the installation completes, it goes through a short additional setup step, but once it's then fully completed, each time you start Visual Studio, you are greeted with a screen like this. And it allows you to open projects which you have opened earlier, which is quite convenient, or it allows you to open projects you never opened, or to create a new project. So for our case here in the exercises, we'll create a new project. And we will select a console application, since this is the most convenient. And as said, if you are using a Mac or something like that, then if you install Apple's Xcode, you should be able to do these exercises as well, since we don't require any Microsoft specific language features like MFC or something like that. We just use the standard C with the STL library, nothing more fancy. So we give it a name, we will call it BigInt, and we can create it. And once it's done, we get the full ID shot for integrated development environment, and you see here the next screen for registration, but you can just close it and it works just fine. If, as mentioned, you have an MS account who want to create a disposable one, you can just do it and enter it. It doesn't cost anything except time and your data. Of course, you can turn at least the data collection partially off. In privacy settings, you can turn this off, and it should respect it, at least if they don't want a big penalty from the EU, I guess. So the mode of this lecture will be looking like this. We will implement a few projects interactively during the lecture, so you will have to connect remotely to this virtual machine and do some exercises in real life, so to say, and other tasks you will get assigned as homework. Homework is always to be submitted 2 weeks from when it was assigned, or to be more precise, it should be done at the over next lecture. So if there is like holidays, then and there is no lecture, then it extends by however many holidays they were. The idea behind this is that you get the assignment, you try to do it, and if you run into some issues, then on the next lecture you can ask about your particular issues, get some guidance that doesn't cost you any negative points or anything, and then the time after that you should then submit whatever you have accomplished. Of course, in principle, you can also ask by email if you have some urgent questions. And practically, it is not a hard deadline. So as long as we don't use something from the homework assignment during the lecture, late submissions are valued the same way as submissions in time. But of course, this happens at your own risk, because some things we will need during the lecture later. So at some point we will choose a implementation or use mine, and of course submissions after that point will not be longer possible. To connect remotely, you will use a tool called VNC. There is a free viewer for that. From the company Real VNC, they make the most user-friendly implementations. There are quite a few VNC implementations which are open source, but for here, since it's like the least cumbersome, we'll just go with this, and as said, the viewer is free. So you can just download the viewer. It needs, of course, installation. Yeah, you can do it right now. So it just greets you with the installer, then some license. I would recommend to add the desktop link. It unfortunately does not create any links in the start menu on its own. This is a bit weird, but if you add the desktop link, you will find it easily, and then you just install it. And after the installation, when you open it, there's just one thing to keep in mind, is that it will try to ask you to log in and to send anonymous data. Of course, we want to protect our data, so we unselect this and go for use without login, or whatever in your language this line here is. And then you can just enter an IP address of a server that runs VNC, and you can connect to it. The data for the connection I will write in the chat so that it doesn't end up on YouTube. Just 1 second, I need to check the IP address. So that's the address to connect. We use a non-standard port, and the password. And that's the password it will ask for. But only connect if you will be doing something. Don't connect all at once. That will just waste bandwidth. When you view the screen over Zoom, it's only uploaded once, and then the server splits it to all the users. With VNC, it's a direct connection, so every viewer gets their own copy and thus consumes bandwidth, which we should not waste unnecessarily. Okay, so that much to the mode, how this will work. Our first project that we'll implement will be a big integer class. So if you have attended the first lecture, or if you have already prior knowledge about C and C++, then you know that a computer in hardware can only handle numbers up to 64-bit if you have a 64-bit CPU, and if you have a 32-bit CPU, even just numbers up to 32-bit. So there are various use cases where you might want to be able to use bigger numbers. And for example, in cryptography, so if you think about it, the ACE encryption standard uses the smallest key size is 128 bits up to 256. RSA encryption use thousands of bits for their keys to be secure. Even more advanced standards like elliptic curves still need at least 256-bit keys to be safe. A pattern that here emerges is, by the way, that asymmetric cryptography needs massively larger keys than symmetric one for the same level of security. And since the computer cannot natively handle such a big number, it is of course an interesting question how this is implemented, how all these cryptographic libraries do this, and the answer is quite simple. They implement an own emulated handling for these large numbers. So operations are not executed by the CPU in a single step or a single instruction, but are executed through code with create many instructions. And we can even see a very simple example of that if we switch our compiler to 32-bit, so x86. I will just quickly rename this as well. Oops. Since we will use this file name for the actual class. And if we switch to the 32-bit compiler, and then just let's make a variable int like null, and run the code. It will need to load some symbols from the debug server, but once it runs, we can see that a 32-bit variable, it can assign in one move operation. You can also see using a task manager tool that our process is marked here with asterisk 32, which indicates in this program that it is a 32-bit program that you are viewing. You can also, where is it here, general, image type x86, and it indicates that it's a 32-bit application. Other tools like System Informer work similarly and allow you to inspect and know what bitness your processes have. And since generally it is desirable for code to be as portable between the different platforms, so between 64-bit and 32-bit, it was necessary to allow someone to write code using a 64-bit variable, which natively could only be handled in 64-bit. So if we switch to 64-bit and run it, we see here again that it does it in one instruction. The instruction is very slightly different, but it's basically the same thing, just longer. And of course here now when we inspect it, we see that it's an x86_64, indicating that this is a native 64-bit process. So what happens if we switch back to 32-bit? In principle, this cannot be done with one instruction anymore, and you will see that usually this now, as you see here, is broken up into more than one instruction. In this case, it's just an add, so it's quite it's an assignment, so it's quite simple. But we can, for example, define another variable and set, and then we just want the sum x plus epsilon. And when we run this, we will see how many more instructions this simple addition requires. And the simple idea is that the number is just broken up into two 32-bit chunks. Each of them can be handled natively by the system, but of course at the very end the results must be combined, since when you are, for example, adding, then you might have a carryover from one chunk to the next, and this needs to be handled properly. And in the assembler code we see how this is done in a reasonably efficient way. Of course, when we switch to 64-bit, we'll see again that the same thing can be just done with one instruction. Actually, it uses, well, the add is the one that does the operation. The rest is just housekeeping and moving of data. So we can maybe switch to the 32-bit version to see which. So we have one add instruction here, then another instruction, and the move instructions around are just for moving data. So if this code would be made more efficient, in this case we couldn't save a lot, but in the case of the 64-bit, let's see. So this move is unnecessary. We could directly write to rax, and here, yeah, it's as efficient. It's reasonably efficient. So of course one can try to see how it would look when the compiler optimizes the code a lot. The problem with that is that one of the optimizations the compiler does is it tries to remove unused variables. So in this case we'll assign a random number to one variable, a random number to another, and we want to return the value. Actually, we could also print it to the screen. That's not quite right, because %d does not work for 62-bit values, but it should be the correct would be, I think, long is the right one. So now if we see how optimized the whole thing was, we have our rand, and then here we have the addition. And the way this here now, it really just does the addition in one instruction after the data have already been put in registers, and then it moves it to the one register which expects the argument to be passed to our printf function. So it even saves operations in as much that it does not write it back to the system memory, just keeps in a register and then moves it to another register. And if we look on the same thing in this 32-bit version, we see that even if it tries to optimize, it will here need just 2 instructions for the add instead of 1, and then it puts the data on the stack a bit differently, since the call instructions, the handling of function calls for 64-bit and 32-bit is defined differently on these 2 platforms. So our goal basically is to something similar, just with C code, not assembler, and in a more user-friendly way, let's say. So in principle, the compiler designers could have implemented everything as such that you could use arbitrarily large variables, but they did not. So if we want to use anything larger than 64-bit, we need to write our own implementation. One thing that one might be curious about is that in modern 64-bit architecture there are quite a few registers which are larger than 64-bit. Even in old 32-bit instruction sets you had registers up to 128-bit. In the SSE instruction set, later AVX, and in the latest CPUs AVX 512, indicating that it can handle a register size up to 512 bits. But those instructions are so-called vector instructions, also referred to as single instruction multiple data SIMD instructions. And the idea is that you have vectors of numbers. So a old 32-bit CPU cannot handle a number bigger than 32-bit, but it can handle a vector of however many, 4 32-bit numbers, and of course such a modern CPU with a 512-bit register could handle up to 8 64-bit numbers or 64 8-bit numbers. So the byte size, the word size in the vector can be adjusted depending on the used instruction, so that you can process large amounts of data efficiently. And in the past, nowadays mostly as well, such instructions are used when you are, for example, doing multimedia compression or decompression. You could use it for rendering of images for AI applications, although here, of course, GPUs are much more efficient nowadays. But those is the type of task where this vector instructions are usually used. And for the general case application, when you're writing a normal program, you would usually not need that. And if you'd want to do some more complex math, some matrix operations, etc., you would usually go for using a library. So those instructions in the general computing case are typically exploited if you want to speed up memory copy or memory assignment operations, because if you are copying memory and you can do it in a bigger chunk, and the CPU, especially if it is able to handle larger memory loads, then it is more efficient than having a loop running and through each iteration copying only 64-bit. If you can have a loop that can per instruction copy 512-bit, for example. Of course, such an optimization would assume that the CPU is reasonably efficient in executing AVX instructions, which some CPUs, the older models especially, were not. So you needed more CPU cycles to complete such an instruction than for a simple 64-bit move. So in such cases, it is of course it has been tested and evaluated which approach is most efficient. But this is just a tangent. We will not be doing such things. I just thought it would be interesting for you to know for which purposes such large registers are used, and why they cannot be used for example, cryptographic operations. So, especially with the RSA case, a 512-bit RSA key would still be far too weak to be used in any practical application. So, it is in any case unavoidable to have some own implementation, and such implementations usually are called big integer, and they are usually made to work with integer numbers. So we don't care for floating point maths when using cryptography. We do everything in integers because we want the operations to be usually fully reversible with the right input data. And of course, without the key, they should be not reversible at all. So we will create a new class. Can use the class wizard here. C big int. It is customary to start class names with a C, just indicating that it's a class object. But for the file names, usually you don't do that. Okay. Since this is a exercises to a part which should happen after part 1, I assume you know what a C++ class is, so I will not explain everything in detail. The task for today will be to create the most basic inner workings of our big integer, so that it is operational, and there will be some simple homework assigned. During the first lecture, you won't need to do anything interactively. During the first exercise, you will just have the homework assigned. So, well, let's start. So, as said, for our application, we want to break down the large numbers into smaller chunks, similarly to what the compiler is doing with the 64-bit number when compiling for 32-bit. So we'll need some data type which we designated our chunk. So for example, we can type def a unsigned long as a type chunk. We could of course use something shorter, like a short or a character. In principle, if we want to optimize for performance, if we are compiling for a 64-bit target, we could of course use a long or underscore in 64, so that our chunk is as large as the hardware can handle it. But since we want to be able to easily test our own implementation, it is more useful to use something that is small enough that we can, for example, we could use a short here, and then we can have a 64-bit number on which we can make the compiler make an operation, and then make our class make the same operation, and then compare the results, so that you can very easily write test cases. Which brings me to a point I forgot to mention with regard to the homework. So when the homework is assigned and you write your solution, you should always provide test cases. So inside the main function of the project that you are working on, you should implement some code which will demonstrate that your solution works correctly. So ideally you provide some test input data, some reference results, so what is expected to be the result, and then you have your code perform this operation and compare the result with the reference result. In fact, this is a practice which, for example, especially in cryptographic libraries, is very common, that those even perform such self-tests always on start. With normal applications, you would not do that, since with normal applications there would be too many things to test, and usually you cannot create simple test cases for advanced applications. But for example, for such a big int class, it is quite easy to just generate a few random numbers, add them, subtract them, multiply them, or divide them, or something, see what comes out if you use some implementation you know that is reliable, and then you just have already your test data. So this we will expect to be in every project. Ideally, it should be enough to just run the submission and see whether it works or not. So the test cases should also write to the screen OK or fail on each test that they run. And of course, don't try to just write something that just writes OK to the screen without doing the actual work. I will still be reviewing the code by hand, but it helps generally to see if it works correctly and it looks okay, then it doesn't need any further review. If every code would need to be manually reviewed for all the edge cases and test cases, that will of course be significantly more work, and we should avoid that. Okay, so let's continue. So we have our, for now we will go with the long as a type chunk. So let's now create some construct of our class. Of course, want it to be public. We can use a, first of all, we'll create an empty an empty constructor which just creates a new instance of our class without anything. And then next we will add a template based constructor that can handle different input types. So it is more convenient than to have like having 4 or 8 constructors for every signed, unsigned, chars, signed, unsigned, short, signed, unsigned, long, signed, unsigned, long 64, etc. So instead we make a template, type name team, constructor t value, and then we will do something here. The idea is, as you probably know, templates, that everything that will be compatible with our internal code will be able to be used as an argument. So this just makes things more convenient. It will make a virtual destructor as well. We don't technically need it to be virtual, but in case we want to extend our class at some point with something, it's more convenient for it to be there, and it does not really impact the runtime of the code significantly. So as you might know, if you have virtual functions, they always take a detour through a jump table, but they just run more instruction, and on modern systems this is negligible overhead. You could make all your functions virtual, and you probably would not even be able to reasonably measure the difference. So the difference will be just swallowed by all the other overhead and timing in unexactness, let's say, of the system. Okay, so this much to this. Now we will want to define some internal objects where we will store our chunks. We'll do that as a protected variable, so that it cannot be directly manipulated from the outside. So if you want to manipulate the data, you will be supposed to use the provided operators and functions. And for ease of use, we'll make the whole thing as a structure. Why we do it as a structure instead of putting the variables directly here in the class will become apparent in one of the later homework assignments, where the goal will be to rework the mechanism this works slightly to optimize on data copy operations and stuff like that. And then rewriting everything would be more cumbersome, but it would not bring you pedagogically anything. So if we start with the data confined to a struct, we already save some later work. And this is, by the way, an important thing in programming. You usually should try to avoid unnecessary work if you can. So it is not necessary to make things always the most complicated and difficult way. Just try to find a way which is efficient enough for your application, and most important, needs the least work on your side. So like wanting to one might want to like write everything from scratch, but sometimes it's easier to just use a library somewhere which already provides the necessary functionality, even if the library might not exactly fit your use case. Okay, so we can initialize this with 0, and then we will want some data stored. So the chunk we will just here have enough room for one chunk, but we'll use a trick to extend this later to arbitrary sizes. Now what we need to define is what usize will actually refer to, because in principle it can have 3 meanings. It can be the size of the integer in single bits, so how many bits it has. It can be the size of the integer in bytes, or it could be also the count of chunks which we have. For our use case, I think bits is usually not something one cares about, and also there are practically no real applications where you would want a integer which is not a multiple of 8-bit, so we don't need to count bits here. And for chunks, this might make things more complicated if we want to change chunk sizes often. So we will define that our size is in bytes, and that should be good enough for our use case. Okay, now we just need a pointer that will point to this thingy. And we initialize this with null. So when the whole when the whole class is instantiated, the thing will need to be created before it can be used. And in other functions which might refer to this, we will always need to check whether it is actually instantiated or not. So for example, we would like the tchunk asterisk raw data function, which will give us the raw data. So zack per data or null ptr in the else case, and then something similar for the size. We call it raw size. Of course, here we need a different type, size and or 0, and we can define this as const. This means that inside the function we are not allowed to alter things, and it means also that if we have a const pointer or const instance of begint, we can still use this function. So non-const functions cannot be used on variables which have been defined as const, for simple reasons that we want to avoid modification. This is of course not a hard limit, so there are ways you can easily cast this on a non-const version and then still do modification, but we will not be doing such things here right now. Okay, so we have this, so we can fill it in with some life. So this the first begint, which kind of doesn't do anything, can stay empty. For the destructor, that we will take care about in a second, but the first thing we need is our begint here, which will take arbitrarily sized variables, or within at least what the CPU can natively handle, and create us a big int from that. So for test cases, it will be very convenient. You can just create a underscore int64, assign something to it, and then assign this here to the big int, and you will have a big int which is supposed to have the same content of your 64-bit variable, but broken up into 2 parts. Or actually we could also go with short, so that we even broke it up into 4 parts. Actually I can just provide all the options, and then you can just select which one you want. Char, short, long, in 64. Yeah, that makes it easy to switch. And there is also one interesting peculiarity about how stuff is stored in memory, how integers are stored in memory, which we will take a look in shortly. Just to keep in mind that the order of bits and the order of bytes might not necessarily be the way you would expect it. We will see that, as said, we will see that shortly. Right, so first we will need 2 helper functions. One which will create such an object, so we will call it alloc data, and we can make it a void function, since it will just directly allocate this variable. We will not use it to generate something that is allocatable, since I don't think we will need a use case where we will swap things with newly allocated ones. But if we want to change it, this is an easy change, and this takes as an argument size t. So that is all that we need. And then we of course want to have something that deletes it. Alloc, you should write with 2 else. We'll call it free data, which will just free our data. Or you know what? Let's maybe to make it more flexible, we can make it like this. Then you need to type a bit more when you use it, but it is more flexible this way. So zack. Okay, so the alloc first we'll define as a variable which we might fill with content. We'll return it once you're done, and here we will see if size is greater than 0. So if size is 0, then we will not bother allocating an empty element. Also, the way it is defined, it should at least be one chunk in size. Okay, so we will need the count of chunks. So size t count is equals u size divided by size of the chunk, small h. The problem here is that if size is like a chunk and something, then will be this something short, since it's an integer division which drops the residual. So what we need to do is we need to find out if there is something left, and we just do it using the modulo operation. Size modulo. That's kind of the opposite. It just gives you the remaining part. So if this is not 0, then we just increase the count by 1. In principle, since division operations are computationally intensive, there are also tricks how you can make this more efficient, and just instead of 2 divisions, have only 1 division and a addition. But if you want such tricks, you can try to find them yourself. For now, we will go with the more straightforward approach, because the other way of the code, it's when you read it, it might not necessarily be directly apparent what it's doing if you don't know the trick. So this way the code is self-explanatory, so this is the way we will stick with it. So pointer is equals, we need the type. Might notice I'm copying pasting a lot because it's usually faster than typing, but copying and pasting is usually error prone. We need to include here, by the way, something so that we can use malloc. Malloc is a function call which just allocates you some memory where you can specify the size. So we go with again size of big int this time, plus u count minus 1. We know that that count will always be at least 1, since it is more than 0. This might give us 0, but then this will give us something, so it will always be at least 1. And this minus 1 we need because one chunk size is already part of big int, and then we of course just multiply it by chunk size. And since in C and C++ such a structure is represented in memory quite directly, there is no additional abstraction. Whatever last array we have in a struct, if we allocate just more bytes for the struct, the array will just end up being bigger. C++ does not have any built-in mechanisms to verify that such a simple how large such a simple array should be. No bounds checking, which of course makes is one of the reasons why C++ is a bit dangerous when using. It's easy to screw something up and then corrupt memory, which can bring security issues as well as very strange bugs, because things crash independently from where something went wrong based on some data being corrupted, and then when they are used properly they cannot be, and the thing crashes. So Now there are two things what we can do with our allocated memory. We could either just zero everything, and given how this here is made, this is a fair approach. So let's do that. Memset, and we could actually keep this as a reference. So this usize is not the same usize we have in our struct, so because this is the size of the whole struct. Memset, we don't have memset. What was that defined? Windows Edge. I think it's also defined in strings age. Maybe we should go with that. We should try to avoid unnecessary include, since this increases the compile time. Okay, so we have memset everything to 0, so this whole thing is 0. And this is all we need to do here. And our 3, we just need to unallocate. So we have a function call for that here, which will just wrap around. If we add more complexity, we might make this more complex than just one instruction. For example, if we would have additional data stored here, or the array would be allocated separately and things like that, or if we want to call the destructor of the object, etc., it is nice to have this wrapper function. Okay, so since we can already create our data, we shall do so. Here, mptr alloc data size of t, and memcopy data comma address of value. And here we also see that we intend, we need to tell it how much to copy. We see that we intend to have the bytes aligned in our own data structure the exact same way as they are aligned natively on this platform. This is quite useful, because then the content of the t-chunk array can be directly compared, for example, by bit with a 64-bit number, and this makes test cases and testing of the code much more convenient. So let's do it. So we will need to include our big int. Big int. My int, let's call it my a, and the number int 64 a is equals that should be enough. Okay. And then let's make a void pointer raw data, and we're gonna of course also get the size, just to check that it did the right thing. Get size. Okay, and we can run the code. Okay, so this was release build. We want to switch this, of course, to the debug build, since there we get more information about what our program is doing, and nothing gets optimized away. So size is 0. That doesn't seem right. We forgot to set the size. We need to set the size, of course, as well. So we have allocated. Right. We should actually do this here in this function. Zack size is wait, we used usize, so we need to rename this total size. If you redefine a variable inside the new scope, then it will not conflict, just a new one will be used. which might be a bit annoying. That's why usually you can set a warning option in the compiler such that if such a thing happens, that it will warn you, because this is an easy way to get in trouble. So we can actually go here for our C++. General warning level, and set this to either warning level 4, which is more, or just all warnings. Let's go with all warnings. If you want to be particularly hard on yourself, you can also switch the other option on. Treat warnings as errors. Then your project will not compile. And while this might seem like a good idea if you really want to avoid mistakes, when debugging, you sometimes want to comment out a code block or something like this, and unfortunately you also get warnings. For example, if you have a variable which was defined but wasn't used, or if a code block is unreachable, you would also get a warning, in which cases disabling code paths for debugging gets more complicated. So I would recommend enabling this option only for the release build, where you should not have any blocked out code blocks anyways, at least not ones that are not properly disabled. But having just more warnings is acceptable. We can see how many more warnings we'll get when we run this. Since it started, it didn't show them to us directly, but we can see here that we have quite a few actually. So we should address each of them one by one. But now again we check the size. Okay, size is now 8, which is correct. So 64-bit divided by 8 gives by 8-bit gives us 8 byte, which is the right value. And of course here our data pointer, if we take a look on it, it contains the same data as our a variable. So we have here two memory views. Reference on a. And as you see, these are identical. And as you might also notice here, the order in which the data is written is kind of counterintuitive. So you would of course expect, if you have a number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, C, D, F, that you will see this in memory. But as you see, while inside every bit, inside every byte, the order is maintained 1, 2, 3, 4, 5, 6, 7, 8, and so on. The order of the bytes themselves is swapped front to back. This encoding scheme is called little endian, and the opposite of it is a big endian, where this data would be in the right order. Well, in the right order from a human perspective, I might add. The reason why this is done like this is a small optimization which can bring a lot. Namely that if you cast a larger variable on a smaller variable, so for example if you cast this whole 64-bit number on a 32-bit number, then you can just copy the lower bytes, and this way it's simpler to implement internally in the CPU, because you are just you always start at the same address sorry, the other way around. You just copy the lower bytes, these ones. So you always start at the same address and just copy however many bytes from the cell. So if you cast to a char, you copy 2. If you cast to a short, you copy 1. If you cast to a short, you copy 2. If you cast to a long, you copy 4. And if you cast to a long or in 64, you copy all of them. So the starting address is always the same, and it starts with the least significant bytes. Generally, if you are using loop variables or things like this, you always care for the least significant bytes. The more significant bytes will only be relevant if you would have more elements. And in various applications, even if you if the interface or the API uses 64-bit numbers in modern systems, for many applications a 32-bit number might be just long enough. So if you have some older code or generally just want to save on memory, you might opt for using 32-bit numbers and doing such casting. And because usually you expect the higher order bytes to just be set to 0 anyways. So this is one of the reasons why they selected such an counterintuitive order. that everything is swapped. There are functions which allow you to change the bit alignment, but then if you want to do something with the number, you need to change it back, so it's of little use. The main reason why such functions exist is that often in network protocols, the byte order is defined to be large endian, for historic reasons mostly, and thus it is helpful to be able to quickly convert between those two representations. But as said, for any practical interactions with those numbers, you would usually then want to have them in the little endian format. Okay, so we have seen that our very simple implementation is already doing what it is supposed to do. We can of course check this also programmatically in 64. A2 is equals, then we will just cast this to a in 64 and then dereference it. And now when we run it, we have here, as you see, more different tabs, for example locals, which shows you all the local variables. You also have watch 1. Here you can basically locals and watch 1 works the same way, just that local shows you everything local, while watch 1 shows you only what you want to see. And you can obviously, as the name suggests, add more watches, so you can add some watch 2 with some other set of things you're interested in. Where was that? Yeah, watch. You can add up to 4 watches if you want. But here, and one other thing, there is a button here, but I think you need to enable it. Here, it's on the, what was it, build, debug, on the debug tool. And if you press it, then it will change the representation in all these different views to hexadecimal. So you see now, we see the hexadecimal representation, and we see that these are correct. So to complete our test case, of course this could be a bit shorter, we could just directly take this, but since we want to make a really good test case, so first if size is not equal of size of A. So size of, as you might remember if you have already some C experience, takes either a variable or a type. It works for both. It just gives you the size in bytes of whatever you have, if the size is known at compile time. So for example, size of this is always size of this with one chunk. If we allocate this with more than one chunk and make size of on the variable, it would still give us only the size of this based on the type. It would be completely oblivious to the fact that we've allocated significantly more memory in addition. So this is just a cautious tale about the limitations of size of. So if this is not right, then we can already printf. Printf wants an include hash include stdio. Of course, instead of printf, you could also use cout, which is the more modern version, but since the lecture is called low level, or the exercises are called low level, so we will try to use the most basic things. So how do we format the message nicely? Let's say failed, yeah, exclamation mark and semicolon, else we can continue. So we check that the size is correct. In principle, we should also check whether the thing is not null. I mean, it's kind of, when we know the code, it's impossible for this to be null while this is not. But since we want a very generic test case, it's formally we should also test for that. So we test if this is failed, data is null. So we have already captured 2 mistakes, and now when we know the size is correct and we know that data are valid, that is more or less as much as we can test. The data could still be a non-null variable pointing to an invalid memory address, but that we won't be able to easily test. So we make here our test case, we make the assignment and the dereferentiation, and now we check if A2 is, let's go say if it's not equals A, then failed data A is like A2 or something. Just write what you want. Big A2 data wrong, something like this. And else everything went right. So we should also add like fail. In principle, you can add special control characters to the string to switch text color. So if you want, you can make fail be red and pass be green or something like that. But that's up to you. There was one case which we have not yet error handled. That is, what if, as I mentioned, this is some garbage memory. So we can do that. This is equals avoid. Actually, we can be. We just cast the content, which definitely is not a valid address. And now, if we try to run it, the application should crash. And as you see here, the debugger catches the exception and shows us what happened and where and why. So it says exception thrown at address. So this is the address in memory of our code. C005 is access violation. Reading location. For whatever reason it tried reading FFFF, even though this is not quite FFFF, but nevertheless it throws us an exception, so we see something went wrong. So can we somehow handle this? And in fact we could. We need to have this. Let's initialize it and try. It will actually work with normal exceptions. It should not necessarily catch system exception. I should have tried it before. Notice exception settings. The way this works is that the debugger can catch also caught exception. That doesn't work. I don't know. Let's use the other trick. Try what was this? There are some defined values how you can make this exception handler handle. So what you can make it do? What was the name? Because we have three options. We can retry the same instruction, which will just crash again. We can not do anything, so let the application crash, and we can say that the error was handled. So we go with exception. Continue execution. That thing needs to be included. Except H. Wait, there's a typo. Except H. Now it should work. Exception. Right. So execute handle. Let's go for execute handler. Execute handler will execute this code, which is none, so this should be okay. This of course also annoying. We need to wrap this in a C function. Extend C. Save. Call it safecast. Safecasting in 64. Safecasting in 64. And this will just contain void asterisk pair p data. So you cannot use all the features in all the languages. For example, here you cannot use try exception easily inside a normal C++ code, but you can make it in C code, and here we have just then return 0. We could also have a, actually that would be more convenient. Okay. 64. Oops. E. Return E, and oops, E not 1. Return E. Asterisk okay is gleich true. Here okay is false, so that we know that something went wrong. Okay, so we make it like this. Per Data und Referenz auf okay. Semicolon, and if Wegschickt okay, then fail per the valid address else. Okay. Yep, and now it works correctly. So we have pdata is not a valid address. So if this operation fails, the operating system catches the exception, redirects the first. It executes this handler code, which just tells us to execute this. We could have here actually a function call to evaluate and decide based on additional provided informations, but we don't care for that. Here we then just say that it failed and return 0 because we need to return some valid value. We could of course also kind of try to wrap the exception then in a C++ exception. That is what you saw me earlier do with this try catch without the underscores, but that works only with a subset of exceptions. It doesn't work for every single one, and apparently it doesn't work here for this one either. We can reset defaults to see if how this will be handled now. And as you see here, if we reset this, it is able to catch the exception. But here, in fact, you can now play, and it will continue. So if you are caught in an exception in the debugger, if you press play, it will do one of two things. Either it will just continue if there is a handler, because then it will as next execute the exception handler, or it will actually then just give you the same exception because we just try to retry the operation, and it will never succeed. So often if you are caught in an exception, the only thing you can do is just to terminate the program and then fix the bug, and only once this is done, continue with your code. Of course, the whole thing here could be made even more elegant if we would put it in a function which then printf error and return. Then we would not have multiple levels here of nesting, but this for this application this is good enough. You can implement the test cases however you want, as long as they work. And since we have this working, I think the next task will be to look for some reasonable homework. And one thing that obviously we will need for our number is some other ways to fill it in. So for example, it would be very convenient if we could feed a hexadecimal number to the class from a string, and it would create for us a from this hexadecimal input. It would create for us the content, the input for what we want. So let's do that. Bool from hex. It will take a const char asterisk string, and that's it. So it expects a normal null terminated string. We could of course make this as a constructor, but usually this is more convenient. And we might for later also want to create some assignment operators and so on. So for now we will make from hex, and of course we would want it to be able to print the number to screen. So obviously as long as it's just 64-bit, we could just do the casting and then print it with printf. So pass, actually I can demonstrate it, %null x. we want to look at nice. So null x comes as a prefix, % null 16x capital and long comma a2 is our correct value. We can quickly run it. Right, we should fix the purposefully introduced bug, and it didn't work. Was that LLX? No. Yeah. So as you see, it works quite easily, but of course we would prefer this to work also with much larger numbers. So, for example, what we could do here to feed it a bigger number would be to create a struct s int 128, which has int 64, and we remember the right order. So first is the low byte, low q word, and then comes the high q word. So we have our number. This is, by the way, how people what people use basically when having very old Windows versions which only had 32 bits, no 64-bit support, and did things with the file system, which already back then supported more than 4 GB of file sizes, or at least in certain scenarios. So you had used such structures which splitted up everything into two variables, a high and a low one. Let's call it just b. And we need to, of course, initialize it. Of course, we cannot assign just one number, so we need two. So first one is the low one, and the high one, we don't want this to be 0, so let's go with, let's do it like this. We just make 1, 1. Wait, that's too much. It goes until 8, 0x. Okay, this will give us a nicely recognizable number. We can quickly test it, how it looks in memory if we have done everything right. Memory reference, and we see no, we did not. It was supposed to start with the F's, so we have high. Does the high word goes first? Alright, that's the. Yeah, I just switched this here. So first we want the low one, and the low one is the one that ends with the F's, and the high one is the one that starts with 1. Now it's correct. Zack. Reference B. Oops, reference B. FFE, DD, BBA, and so on. Yeah. So this is now one way to make such a number, and in principle, when we feed it here, my B, that should actually work. So we could size, well, B, data B. Zack. Wait. Oh, sure. That's the dangers of copying and pasting. You forget to update all the things that needs updating. And as you see, our class is already properly handling such a case. But now, of course, we are lacking a way to print it. So the homework, as mentioned, will be to make a from hex, and then, of course, a to hex function. Oops, to hex, and to hex will take a char per string, and it will take a size t o len. So here we expect a null terminated string. So as we read the string, we can find where it ends, and thus not process too far. In this case, when we are creating a string, we are writing to a string, we could of course just assume that this will be large enough. But such an assumption is dangerous because it might be wrong. You don't know what someone that uses your library will do. Maybe they will allocate just a few characters, and there will be cases where will need more, and then they will start overwriting some memory they should not be touching. So the proper safe approach whenever you are writing to an array is to provide a variable that specifies the maximum length of the array. In principle, it is also good practice to provide a length even if you're just reading from an array, because if you are relying on a value in the array, like the null in a null terminated character string, what if the string is misformatted, if it doesn't have the 0? Then you will run in one of two scenarios. Option 1, you will read past the end of the string, read garbage until a random 0 occurs, and then nothing too bad happened. You will still have garbage data, but at least the thing didn't crash, which actually might be even worse, because if you have garbage data, you might not know what your application will then do next. Or the other thing which might happen, it will just keep reading until it runs out of the valid address range, and then causes an exception because it tries to read a memory page which has not been allocated for this process. So, for example, if we want to be convenient, what we can do is we can do it like this. So we provide by default an invalid value, -1, as an argument, and the idea is if we just provide string, it will check is len -1, and if it is, then it will retrieve the length from the string through a function that just is looking in the string for the terminating null. But if it was provided a length limit, then it will just read until then and not require the terminating 0. So these two functions we can let's give them that's a good place. Let's put them here and at least provide some very basic skeleton. Of course, we don't do that once we are here. So here just one small thing. So if this is equals -1, then this is equals len pastor. Okay, and this one of course will have to do something on its own in the homework as such, and of course return false because it's not implemented. So to do, or let's call it homework, from say 0 to 10 to 0 to 5. From x or not. And the value or this object data true. Should accept upper and lowercase characters on value i.e. invalid character not 0 till 9 a till f a till f it should return false. Okay, so this function will need some error handling and so on. Of course, the prefix 0x, the x is only allowed in the prefix. That's why I didn't mention that here. And of course, the next one, 2 hex, is pretty much the opposite. Homework 1, homework 2. Implement this function. It should. That's the next question, with or without prefix. Let's call it B prefix. since it should to its hexadecimal null x, and in we needed a second optional parameter specifying if we prefer upper or lower case. Lowercase false, uppercase looks nicer, so the default will be uppercase, although not all libraries and conventions follow this. But usually, since the parsers don't care, it doesn't really matter, just for what looks better, but I think uppercase looks better. Yeah, it should convert to the uppercase, and that's already kind of it, because there is no error handling, nothing, you just assume the thing is correct. I can add one more line. If so if the thing is 0, you can, well, return the right length of zeros. So the way the thing about hexadecimal representation is that usually when you use it, you should pad it to the full size. Actually, I should add this here, and you could make it optional as well. So prefix and no. So if no padding would be set to true, then it would not pad the values. 0, 0. Two. No padding. Then truncate the leading zeros. This will add a small layer of complexity, but it's not really difficult. So any questions? Okay, there don't seem to be any questions. So this is this. I will upload it to Moodle, although we have 5 more minutes. So maybe I can demonstrate you how such a test case should work. So for example, pool test hex, just call test hex. Okay, so we move this here. This we will call our int 128 my int 128 from int 128. Oops. Then we have something. Then we can const char stern per hex. So this is what we expect. We could skip this. We could just initialize it with 0 first. Although we need this. Let's skip it. So first, the easier thing, I guess, is 2 hex. So let's first test if this works. So const char stir test. Oops, stir test. How big do we want this to be? How many do we have here? Well, we know how many we have here. We have 32 plus 2, it's 30. Is it 30? It should be 34 plus a 0 terminating character, 35. That should be the right length. So we have our punkt to oops my int, this one, to hex thing size of and the rest we leave as is, uppercase why doesn't like this. Oh sure, it should not be const. We want to be able to change that, and it doesn't return true or false, so we just check if sample test string with string test means string hex. If this is 0, it returns 0 if they're matched. Then actually we want to bail out if it's not 0. Otherwise we continue with the next test. So big int to hex failed. Output comma expected %s got %s. Expected test got hex. Rightio, and return false. Okay, so if this worked, then one function worked. So now we will do the opposite. We have here my int. We should create a second one. My test from nothing, and if exclamation mark from hex, we just paste it as is without anything else. If this not, then from hex fail. Oops, we should. No, that's fine. Yeah. Fail. Okay, so this works. We could add a second test. It's the bad hex. Q. Let's add a few invalid letters somewhere. Especially an O looks very suspiciously like a 0. So it's a very good candidate to break something. So actually our approach would be, first we test the wrong one, and if it succeeds, return then we try the right one, return false on valid input, and now we test if it's correct. If sample, it's like string cmp just for memory. We have my string, which is supposed to be correct. Get data, comma, punct, not my string, but my test. Get data, comma, size of my test. Get size. You already see here one potential issue. Or if this is not that we only specify one size parameter, even though we have two pointers, which already is a potential source of a problem. So here from hex failed, result invalid, and here I know we are starting to get over time, but since we started 5 minutes late to wait for a few people, let me just quickly finish this. And so we need to add one more test here, which compares the sizes first, so that we know that row size of my int will be the same as of test int. So this, if they are not equals, get size result has result size mismatch. Okay, that's it. So this is a test case that you can use for future homeworks. You should use such a template, such an approach to write your own test cases. Here, actually there is no here. The test case is complete. But as said, what you need to implement are those two functions and the test case. Of course, the test case might contain a bug, so if it does, then it's an access for you to find it. So yeah, that's that. And since we're over time, I think this is a good point to finish. I will upload the recording to YouTube. I will upload the project and the homework assignment to the Moodle. If you have any questions between the lectures, you can email me at any time. And for those that participate in the lecture part 2, that will be at 3 o'clock. We will see each other in 3.5 hours. And for that who don't participate, we'll see each other next week. Bye bye.